Hello everybody, my name is Emir and I'm an engineer working for Microvi in Sarajevo. Unfortunately, I'm not able to be with you today. I'll be sharing my presentation with you via this pre-recorded video. I hope you'll enjoy. This presentation is about a vibration monitoring system that we developed here in Microvi, and I'll be doing a brief overview of its key features and the main challenges that we faced while developing it. We have developed this system for acquisition of acceleration or vibration data of a mini hydro plant. Why would one want to capture those data? We want to capture those data to predict if something is going to break soon in the future. We want to change a part that's going to break soon before it breaks the downtime of the mini hydro plant. We want to avoid at any cost. That's the reason for developing. There are a few key components of the system. It consists of 4 vibration sensors that capture acceleration data. Next, it has 4 transducers which take the input of the sensors and send it further down the signal chain. After the transducers, we have an analog front-end PCB which takes the signal from the transducers. After the analog front-end PCB, we have a host board, but it's basically a PCB which houses a microcontroller, which is used for digital signal processing and communications. Then we have a PC, which is running a database. The PC doesn't need to be present there at the mini hydro plant. It can be at some remote location. And then we also have a Grafana server running on the PCB, which can be used for easy visualization of the data. The system specifications. We are mainly interested in vibration frequencies up to 1 kHz. From 0 to 1 kHz, we have 4 measurement channels. That number corresponds to the number of vibration sensors. We have a sampling frequency of 10 kHz. We believe that is more than enough according to the Nyquist criteria. We are recording the analog signals, performing ADC, and then performing digital signal processing of those signals. Here are listed a few of the steps in the DSP signal chain. We also have an Ethernet link running between the MCU board and the local or remote PC with configurable transmission times. We can transmit every 0.1, 0.5, and up to 5 seconds. Additionally, we also have a database for storing the data on the PC, and for graphical visualization, we are going to use Grafana. Grafana is hosted on the same PC and should be available over the internet. One of the main reasons why we are going to use a database for this instead of just visualization of the signals is that we want to use machine learning so we can more reliably predict future failures before they happen. Here is a block diagram of our system. On the far left, we have our 2 possible sources of vibration. The top one is a vibration calibrator, and it's used mainly during testing. Beneath it, we have a rotating generator as a possible source of vibrations. We connect 1 or even 4 of these sensors, and each sensor comes along its own supply module. We'll talk about it later, why it's needed and why it's there. Next, we have analog PCB, which does some signal conditioning. Signals go to the MCU PCB, which communicates with a PC, which has a database in the cloud. As a last step, we have visualization in Grafana. We're going to talk about vibration calibrator, the VC10. One of its main specifications is that it has a constant vibration acceleration of 10 meters per second squared. That's a RMS value. It has an amplitude of about 14,14 and a fixed vibration frequency of 159.15 Hz. This vibration we are expecting. It has a precision of plus minus 3%, which is good enough in this case. Now let's talk a bit about vibration sensor used. It is the KD37 integrated electronics sensor. It requires a DC supply voltage of 5 to 14 volts and it sinks 2 to 20 milliamperes. The connection is made via a coaxial cable and the upper frequency limit is 7 kilohertz. And one of the main characteristics of this sensor for us is sensitivity, which is 5.745 millivolts per meters per second squared. The interesting thing about these kind of sensors is that its power supply and its output actually share the same line. So a DC voltage and the AC voltage, which is a result of vibrations, actually are superimposed on a single line, and all we need to do is to separate the DC signal from the AC signal, which is done by nature of using a series capacitor. Let's talk about the supply module, which goes along every vibration sensor in our system. It has three functions. It acts as a supply for our sensor. It can supply from 3.8 to 5.6 milliamperes of current. It needs its own power supply from 5 volts to 26 volts. It removes the DC component using a series capacitor or a AC coupling capacitor. It has a bandwidth of about 100 kilohertz and we connect to it using BNC cables or BNC connectors. On this image, we can see just a block diagram on how to connect it with a vibration sensor and how to connect it to our measurement instrument. Here we see picture a series capacitor and the output impedance of 220 kilo ohms. So basically this acts as a voltage source, a low impedance voltage source for the instrument that is to come after it. Now we can talk a little bit about our analog PCB. It has 4 input channels and 4 output channels for the 4 vibration sensors in our system. We assume that its input and output voltages are proportional to the acceleration measured. It has a main function to scale down the industry standard -5 to 5 volts to the 0 to 3.3 volts. 3.3 volt range is centered about 1.65 volts, and that represents the input range of the ADC on our host board. Here we are mentioning a voltage range of ±5 volts, and that is industry standard for vibration sensors. We designed our system in accordance to that. The left image shown on this slide is taken from CAD software, and the image on the right is a similar board. It represents the case that will be used to house this particular analog board. Even though the output of the M28 supply module already has the DC component removed, we also included a DC blocking capacitor in the schematic of the analog board just to be able to use other system which does have a DC component present. After the DC blocking capacitor, we have a op-amp circuit, which is a non-inverting op-amp with offset, and also the offset is generated by using this 1.65 precise reference IC. At the output of this op-amp circuit, we get the desired 0 to 3.3 volts output range. Here we see actual measurement of our board with a oscilloscope. So the yellow graph represents the ±5 input sinusoid. Blue graph represents the actual output of our analog board. Here we can see Bode plots that are recorded for our analog board. They contain some outliers, but we get the whole picture anyway. So from the magnitude plot, we can see the analog board does serve as a high-pass filter. We see that the lower frequencies are more attenuated than the higher frequencies, which is something that we expected. And from the phase diagram, we see this little outlier at lower frequencies. It doesn't look like it's going to reach the -180 degrees phase, which means that our analog board is relatively stable. Let's address the PCB which has our MCU on it. Its main characteristic is that its ADC is a 16-bit resolution, and we have configured it to sample our data at 10 kilohertz. We perform digital processing. We do mean removal to perform integration more easily. When we remove that mean, we remove the 1.65 volt offset that was present at the ADC input. The mean removal helps in filtering the data. It removes some of the high frequency noise as well as the low frequency. After this filtering and mean removal, we perform FFT on each of the 4 channels. The length of the FFT is 1024 samples. All of the standards of vibrating systems talk about velocity of the vibrations, and the signal that we have measured so far is only proportional to acceleration. We need to use firmware to integrate in order to get velocity data. We performed integration in the time domain. There was still some DC component present after the integration which corrupted our data. So in order to not have that mean present in the integrals, or to minimize its impact, we decided to perform the integration in the frequency domain. And then to obtain the integral, we just need to perform a reverse Fourier transform. In order to more efficiently copy those data, we decided to use DMA. The ADC is sampled using a timer with a frequency of 10 kilohertz. The RMS, max, min, and FFT bins for all 4 channels are transmitted via Ethernet to the remote PC. And here we can see a live plot of the signals that the MCU is transmitting. The frequency of the measured vibrations was 50 Hz, and that's why we see a peak at about 50 Hz. And on the lower 3 plots, we see the RMS values for each of the 4 channels, the maximum and the minimum values. And the MCU PCB has Ethernet connectivity via the LAN 93053 PHY chip. We needed to develop the Ethernet driver for it because there were no ready-made packages. We transmit the measurement data to the PC via UDP, and we also transmit a heartbeat message every 5 seconds via TCP, telling the PC that we're still alive. The PC can make sure the number of messages that it received is the same as the one that the MCU has transmitted. A configurable transmission period of every 100 milliseconds up to 5 seconds. And the MCU will be mounted in the same plastic case as the analog board. And both of these boards will be placed on a DIN rail next to each other and connected via terminal blocks. Now let's talk about the PC, which is running a Python script and a database. We're using the InfluxDB database. The reads and writes to the database are handled using HTTP requests. We have a Python receiver script running on the PC. Its main duties are to collect the UDP packets from the MCU containing the DSP data. It collects the TCP packets from the MCU containing the heartbeat messages and formats the data into a format that is acceptable for the database. The database expects a set of measurements received from the MCU or a heartbeat message. Grafana is running on the same PC and gets its data from the Influx database for all of the 4 channels. For each channel we get RMS value, maximum, minimum value, and the velocity of the vibration. Also we have 512 points magnitude of the FFT. And the frequencies that are covered are up to 5 kilohertz. The 5 kilohertz is 10 kilohertz divided by 2, and this is because of the Nyquist. Here we have a diagram which shows the FFT bins for channel 1. Here is a visualization from Grafana for the RMS, the maximum and the minimum values for all 4 channels. These plots are captured during a testing procedure where we are generating increasing amplitudes of vibrations. And here is a screenshot from the ISO standard, which is used in order to quantify the amplitude of the vibrations measured. We see that our system falls into machine group 1. And if we look at this graph, each time the vibration falls into this is amber color. Into this category, or in the red or D class, the MCU needs to send the error to the Python script to alarm it, shut down the mini hydro plant because there's some unwanted high amplitude vibrations. Our plant falls into the category of machine group 1, which are large machines with a power output from 300 kilowatts to 50 megawatts. The error messages are transmitted using the heartbeat messages every 5 seconds. Now we will cover the validation procedure. The goal of the validation is to verify that our acquisition system measures data reliably. We have several steps that are in our validation procedure. First is to generate the voltage of a known amplitude and frequency. And by doing this, we mimic the output of an acceleration sensor. And in our case, we are generating a sine wave in the range of plus minus 5 volts with frequencies up to 1 kilohertz. This will not be a fixed plus minus 5 volts range. It can go from plus minus 0.5 volts all the way to plus minus 5 volts. And the frequencies that are covered are from, I believe, 10 hertz to 1 kilohertz. Then the next step is to scale the voltage down to a 0 to 3.3 voltage range using our analog front-end board. And then we acquire the data using our MCU board and perform DSP analysis on it. Then we send that data via Ethernet to the PC. And the step 5, which is actually our custom validation Python script, it reads data from that database and compares the values that it has read to the ones that were generated in step 1. And after reading those values, it should generate a textual output, which tells us if the readings from step 5 and step 1 are within tolerance. And it does this for all 4 channels and all measurements for the RMS, maximum, minimum values. It also peaks in the FFT bins. You can see a block diagram for a validation procedure. It is very similar to the actual system that's going to be deployed. The only difference is that instead of using a vibration sensor with its dedicated supply module, we're using a Moku Go device, which can generate voltages at its output. It's controllable via a Python script. We had luck that the output voltages of the Moku Go to the plus minus 5 range, which is industry standard output for vibration sensors. All of the steps from the analog PCB to the Grafana visualizations are the same as in our actual system. It can be programmed using Python, and the connection is made using USB-C to the PC. So currently we're only using one output of the Moku Go. We are mimicking only one sensor. We have generated voltages of the combinations that are present in these arrays from 10 Hz per second squared to 600 meters per second squared. And this 600 roughly correlates to the plus minus 5 volts output given this sensitivity, and also for frequencies from 50 to 1 kilohertz. Here are some images from the oscilloscope for different frequencies and different output voltages on the Moku device. We are using one analog output to feed 4 ADC inputs, which is not ideal, but it proved satisfactory in our testing. The MCU performs the exact same analysis as it does on our actual system. The same functionality is present in the Python script, which stores the data into the Influx database. On this slide, we can see the output from Python's validation script, and is the one that generates all of the voltages and reads back the values from the Influx database. And here we can see that for a combination of 300 meters per second squared and 50 hertz, we are getting values for the RMSs, the maxes, and the FFTs. We have quite low deviation for RMS, worse deviation for the max and min, and we have successfully found the peak in all of the FFT bins. Here's some of the future work that we are planning to do. The first one is to perform machine learning on data that we are going to acquire by placing this system, by installing our system in the actual mini hydro plant and capturing a lot of data. And that machine learning can be used to generate a C code model, which can be run on the MCU. So we can predict failures before they happen locally on the MCU. And one thing that we can do is perform calibration of the measurement system in order to reduce deviations in measurements. Yeah, which let's say the easiest form of calibration is some linear interpolation, and that is actually one of the next steps in our development of this measurement system. And if you have any questions regarding this system that we have developed or this presentation, here's my cell phone number and here's my email, and feel free to contact me. Again, I'm terribly sorry that I wasn't present in Tuzla today, but I'm happy that I was able to share this, let's say, our work, even if it's only via video. Thank you all for having me, and have a good day.